Thanks a lot, Manjit. And so it's a pleasure for me to introduce you the speakers for the last talk. She is Eleanor Blakely, a retired senior staff biophysicist with 47 years professional career at the Lawrence Berkeley National Laboratory. And her research dealt with molecular, cellular, and animal radiobiological topics, directed at studying the basic mechanisms of radiation responsive, with an emphasis on charged particle radiation effects. And of course, she's also recipient of several awards, and I would like to mention the 20th Gray Medal of the ICRU in 2008. So, Eleanor, it's a pleasure for me. I will give you the floor for this very nice and amazing last talk of this session.
Thank you very much. I really appreciate it. Hello, everyone. I wanted to begin by congratulating each of you for being accepted to participate in this very special course. I looked at your program and it's a very wonderful resource for you. My part in the course is to begin the work that we did in Berkeley about the field of biophysics. And so I'm eager to show you, let me see here. First, I must tell you that I have nothing to declare, but that I have support only through affiliation with, no support, but only affiliation with the Lawrence Berkeley National Laboratory, from where I have retired. But I also hold an affiliation at the School of Medicine. And I am in two departments there, radiation medicine and basic sciences. The goal of my presentation this afternoon is to provide you my historical perspective on the preclinical and phase 1-2 trials that were conducted using charged particle beams for the treatment of cancer in Berkeley, California. And a story to start in the 30s telling you what happened in Berkeley, but the work of this program started in 1952 and was concluded in for those involved in this kind of research to understand these are all my personal insights. My institution is not commenting on this. It's only my insights for the path forward for particle biophysics and hadron therapy. It turns out Berkeley Lab was 90 years old last year in 2021. And that was a huge milestone for us. It has been a long 90 years of various decades of different kinds of research. But a lot of what had begun was the work of the Ernest Orlando Lawrence. He was the physicist that was hired in 1930 at the UC Berkeley to be a physics professor. And he was given an old building to start his work. Let me just try to show you some of the old buildings. His building was called the Rad Lab because he did radiation work, and it was established on the campus in a very old part of the town. And what he's most noted for is his invention of the cyclotron. He invented the cyclotron in 1931, and it won a Nobel Prize in physics in 1939. It was actually the thesis work of Dr. Livingston, which is incredible to me that one thesis could result in a Nobel Prize. It's incredible. But his first construction of a cyclotron could fit in the palm of your hand. It was a 13-centimeter diameter machine that actually could accelerate protons to 80,000 volts using less than 1,000 volts. He was noted as the Time cover in 1939 for that prize. It's one of my favorite photographs of him. The pioneering days in the Berkeley Hills was extraordinary. This is a picture taken from the hills in Berkeley looking towards San Francisco, and you can see in the far background the Golden Gate Bridge here. Can you see? And this space in front on the hill at Berkeley is where he decided to build his 184-inch cyclotron. He had started with these smaller versions to test feasibility, but he scaled up to the 184 for the purposes of which he wanted to study clinical results. Just a second. I'm just going to flip through some of these old photographs that are historically restored. You can see the old cars in the front of the framework of the 184-inch cyclotron, which, by the way, is the size of the D. Here, the roof was being put on, and finally, its composition together. Inside the D, they often took photographs of the whole crew, and Lawrence is seated there in front with his men, and as often as they could. They didn't work in suits, but they definitely were very proud of this device. So it was actually constructed in 1947, and the first beam was produced on November 1st in that machine. Here's another version. You can see quite a few people in the military here in the front, and also young people and old people. It was a very much a team science that was done at Berkeley at that point. Now, turns out Ernest had a brother named John, whom I have had the privilege to know. When I first came to Berkeley Lab, I met him. He was the director at the time. And Ernest felt that once he had devised the cyclotron, he really wanted it to be used for medical purposes to help mankind. And it turned out there was a gentleman who had lost his son to cancer named Donner. And Mr. Donner donated quite a sum of money to Berkeley Lab to actually establish what is now called the biosciences area of Lawrence Berkeley National Laboratory. Just a second. Don't know why it won't advance. So the brothers worked together for a long time. Here they are at the control panel of the 184-inch cyclotron. And the application of physics to medicine was quite a multidisciplinary field at that time that required two different languages almost. People had to learn each other's specialties in order to be able to accomplish anything. But here is the dedication plaque that is on the building that was constructed finally in March of 1941. And Joseph William Donner was the son who had passed. And the purpose of the fund in the building was the application of physics, chemistry, and the natural sciences to biology and medicine. So the field of what we now call Hadron therapy began with this program in 1938, when they were first used by Dr. Stone for cancer therapy. And charged hadron beams, which you probably realize by now, which include both protons and carbon ions, have more favorable depth dose interaction profiles, which is maximal at the end of their range for clinical advantage of sparing normal tissues upstream and downstream of the peak. And initially in Europe, Hadron actually included proton therapy only, but charged particles included protons, carbon, or any heavier charged ion. But now the term Hadron refers to all. Both macroscopic and microscopic differences exist in the physical properties of these various charged ion beams, and we're going to talk about that in some detail. I really like this image from Marie Curie's work, where she looked at using cloud chamber at alpha and beta tracks, showing the difference in ionization power of the particles. This straight left line on the left side is an alpha particle track with its dense ionizations, and the crooked, jagged tracks are the beta rays. And actually, you can't hardly guess that there wouldn't be differences in biology with this kind of damaged streak being very different between the alpha and beta. So Sir William Henry Bragg actually reported and published what he called the Bragg curve, named for him, in 1903. And now it's well known, although we're still learning quite a bit about the biology. And that is the focus of this recent decade and the next, I'm sure. Dr. Wilson also is credited for providing the rationale for using the Bragg peak for radiation therapy. This is a picture on the day he announced his engagement in 1946. He's the one who first proposed the Bragg peak for radiation therapy. The gentleman on the right is Professor Cornelius Tobias. He was the one who brought me to Berkeley Lab, and he was a physicist who worked with John Lawrence. And this photograph is an historic report of the first proton therapy patient that was treated at Berkeley Lab in September of 1954. You can see Professor Tobias in the background. In the forefront is John Lyman, who's the physicist who did the physics and biophysics for the safety of the patients. And in the rear is Dr. Lawrence, who is always present. They're putting a frame on the head of this patient because they were going to irradiate the pituitary. And you can see they used a rigid device to make sure the patient didn't move during the treatment. So a whole series of experiments were begun in 1948, and human exposures began actually with deuterons and helium ions in 1952. 54, the first human exposure to protons occurred. And then we conducted the clinical trials and had 1,500 patients treated in the period from 56 to 86. Now, the work that they did, heavy charge particle radiosurgery of the pituitary gland involving clinical results of 840 patients, has recently been reported. And in the initial patients, what they found, the pituitary lies here over the roof of the mouth, this little red organ here, and it produces hormones, and actually can aberrantly produce pituitary hormones that cause acromegaly. And they realized after irradiating with 30 to 36 gray in 3 to 4 fractions over 5 days that they could attenuate the abnormal changes that from the excess production of the growth hormone. And this is the years after therapy, out 18 years, showing you the human growth factor reduction in the blood after treatment by this course. And this was reported by Dr. Levy and Fabricant in 1991. They also looked at a malformation in the brain that often happens called intracranial arteriovenous malformation. And it's like a rat's nest of blood vessels that forms abnormally during gestation. And they made the observation that if you actually can irradiate with a very high dose, you can vulcanize the tissues and they totally disappear. And that is very significant because that malformation forms or is discovered in young children as they first stress in sport activity. So you can actually do this irradiation without non-invasively and eradicate, in many cases, the lesion depending on the size. And this photo actually compares a small upper AVM with a large one. And the results are much superior with a smaller lesion, of course. This shows the Kaplan-Meier cumulative obliteration rate for 71 patients using intracranial AVM treatment with angiography before and after. And the doses were 7.7 to 19.2 gray. And this was done with helium ions. And what you can see is that with the smaller lesion, which is this top outcome, the patients with residual malformations was reduced significantly in the smaller lesion, but not so much in the bigger one. The other program that was begun in 1975 was started by Professor Joseph Castro, and it was treating eye tumors. Uveal melanoma is the lesion that grows in the back of the eye, and this is a cross-section from one eye that was unfortunately lost and had to be enucleated. And you can see the lens here on the front of the eye, and this is the retina in the back. The reason the eye was lost was not due to radiation effects, but was because the tumor was so large, it detached the whole retina. But you can see that they actually did some very simple physics on paper at that time to identify where the tumor should be and how to spare normal tissues like the cornea and lens, which lie adjacent to such a tumor in a very small space in the eye. Now, the physics of this is very exquisitely sensitive. And here, these are isodose boxes of dose. And you can see from the high color at 100% dose This is a lesion. Here's the lens of the eye. This is an enlarged CT scan of the eye and shows a globe here with a lesion. And the clinician prescribed a dose box that actually would extend beyond where the tumor is in hopes of catching microscopic disease. But the most important thing is to note that the cold line, the blue, has less than 10% dose. And that's why this is the preferred approach for this kind of targeting, because you spare all the normal tissue behind this treatment. So we worked for many years. This is the first 10 years of results of using helium ions to treat uveal melanoma. We had a very high success rate in the 90s with actually retention of the eye with vision. We only had neovascular glaucoma as a secondary toxicity, which actually has now they've been working on trying to avoid that. But this was a very successful treatment. In addition, we have a follow-up that was done 20 years later. So this is a 20-year follow-up study of phase 3 randomized trial of comparing the helium treatment that I just described to you against the gold standard at the time, which was installing an iodine plaque on the sclera to treat the tumor. And the iodine plaque is effective, but has more toxicity. And you can see that in the cause-specific survival and in the disease-specific survival, the helium treatment is superior to the gold standard iodine. And this, I'd like to make the point that this phase 3 trial is a very important gold standard in all of radiation oncology. And to get to that point, a patient is entered in an arm regardless. It's random. It's totally random, not decided on by the clinician for the study to prove the authenticity of the result. The 184-inch cyclotron actually ended its usefulness in 1986, but 1,500 patients were treated, and they were mostly successful because of the precision, including the use of this stereotaxic chair that was built and designed by John Lyman, which enabled the patient to be rotated. We didn't have gantries back then, but you could actually rotate this patient in many configurations to make access to the tumor and sparing of normal tissue the best. So it began in 1947, I told you so far, and it actually ended in 1986. And now it's been replaced by an advanced light source. We recycle machines in buildings in Berkeley. So this whole building has been hollowed out and now is used as an advanced light source. But now I'd like to switch machines to another big machine called the Bevatron. The American Physical Society recently, in May of this year, declared the Bevatron a historic site. And it was in the hill there, built, it nestled more in the flat part of the hill. And you can see the leaders here of the laboratory, including John Lawrence himself, looking at the model, but the actual construction was completed in 1949. One of the problems with the Bevatron was it had a limit. It was designed for protons, and so it had a limit for the acceleration of heavier ions, which theoretically was designed, they thought, to give more strength to biological effectiveness. So this gentleman, Dr. L. Ghiorso, pictured on the left here, he is the one who should be credited for creating this idea of putting two machines on the hill together. We actually had a pipeline between the machine up here on the top of the hill called the super HILAC to use it as an injector into the Bevatron to pre-accelerate the ions to a higher velocity to achieve what was needed to get the power to accelerate near relativistic energies, these particles for clinical use. In 1971, there was a press conference announcing the acceleration of the first heavy ions in the Bevatron. And they also built, adjacent to the Bevatron, a facility which included not only a treatment cave, actually 2 clinical therapy rooms, but biological and biophysics area, adjacent to the beam lines. So these were the 3 caves. This was the primary treatment room, and they had a second one here, and in between was a biology source room. So in planning machine design, it's very important to plan to have experiments ongoing even after construction. And this is a concept that the clinical world for conventional radiation hadn't really considered to be necessary, but is very important. So if you take the long view of a drone over Berkeley Lab, you would see 4 different machines. And I actually had the privilege to operate biology and biological experiments at each of these. It's the super HILAC that I described, the cyclotron, which is here, and the Bevatron, and the 88 accelerator, which was down here. This is not a cyclotron, that's the stadium at UC Berkeley. So with this assortment of machines, the range of ions and energies was quite extraordinary. And when I first came to Berkeley as a young PhD, just fresh off the block, I was tasked by Professor Tobias with the task of finding which of these heavier ions might be more ideal to use for cancer therapy. And you can see in this 3-way plot that, 2-way plot, but textured with the stopping power LHT on the ordinate and the abscissa showing the range, that we had quite a range of ions. I've actually used uranium ions at this machine. But people often ask me, why did you have to go beyond protons? Why did you need heavier hadrons? Well, what we found was precision therapy can conform to the tumor when you have a bigger range. And with heavier ions, there could be sparing of normal tissues, increased DNA damage in the tumor, increased effects on killing of hypoxic cells, which were prevalent in tumors, less repair of sublethal and potentially lethal damage in the cell cycle, shorter overall treatment courses, because hypofractionation could be possible since you've already spared normal tissues, you don't have to fractionate to spare. And also the neat feature that where you irradiate, you actually have the creation of a radioactive beam that you can use for treatment verification. And these clinical trials, which I'm just briefly covering for you in this presentation, were conducted from 1975 to 1992, which is probably ancient history. Many of you may not have even been born, but the first helium patient was irradiated in June of 75, carbon in 77. We did neon, argon, and silicon patients in trials. And the people involved were Professor Joseph Castro, as I introduced to you, his colleague, Professor Ted Phillips, Jean Quibby, George Chen, and I was in charge of the biology. So to give the long picture, I created originally this plot of Bragg curves with the pristine curves on the left, the extended Bragg curves on the right. These curves in the middle were 4 centimeter extended Bragg peaks, and these were 10. Obviously, not all tumors are as discrete as the sharp, pristine peaks, which require increasing energy, by the way, to achieve the depth of penetration. And you see that we had these funny slopes, which were designed by John Lyman based on the biology we collected to achieve an ISO effect in the tumor. We took a compilation of a large number of cell types that were accumulated from an international pool of scientists who came to Berkeley and used these machines, and determined a lookup chart to actually know what it would take to provide a dose of each of these ions to achieve an ISO effectiveness. We'll talk about that in more detail. What I like to explain to people is that what that did was also give us a range of LAT values, not only at the peak, but also at the entrance. So as for carbon, you have a low LAT at the entrance, and then you have at the peak a range of high LAT here. For neon, you actually get a higher LET in the peak, but at the cost of a higher LET in the entrance plateau. And the same was for silicon and argon. And what I'm going to show you is that the results of the silicon and iron were quite definitive in declaring that these ions perhaps were too heavy for clinical studies, for usefulness. And the way we did that was by using human fibroblasts, tumor fibroblasts, and actually doing a dose response curve in air under aerobic conditions or under hypoxic conditions. And the top panel was a carbon extended Bragg peak, and the bottom one is an argon. And what you can see, the upper curve is the hypoxic, which is more radio resistant, and the lower curve is the aerobic curve. So if you take a ratio between these, you can actually calculate the OER or the RBE, depending on which ratio you're doing in comparison to X-rays. And you can see that the hypoxic curves, the difference between the aerobic and hypoxic curves come closer together with argon, which means at this highest LET of argon, there is reduction of our OER to almost nothing. There's no difference if you radiate with air there or not, oxygen there or not, you get the same killing. But at the expense that the argon is also high LET in the entrance, you lose the sparing of the normal tissue. Whereas carbon, you had minimal entry dose for aerobic cells, but pretty good reduction of the hypoxic resistance in the carbon distal peak. So I compiled all of these data, which are now ancient, but show the trend that if you plot it as a function of LET, and this is a dose average LET, that the RBE goes up and reaches a maximum around 100 to 150 keV per micrometer. And beyond that, each of these lines is discrete for different ions of the atomic number. So you don't get just one big curve, which is frequently shown. It's actually distinctly, you have different lines for different ions. And reciprocally, the OER comes down at the same place to near 1 in this range beyond the peak of the RBE. So to make that clear to a clinician who needs to know how much more effective these ions would be in prescription of his dose for the treatment, we created what we called the biologically effective dose, which are these red lines, which were significantly higher than the physical doses that were measured in the ionization chambers. And that's the importance of biology to this field, is that since you can't actually measure directly the biological effectiveness, at least not yet, there are some tissue equivalent approaches that are approximating that. But at the moment, you really need a biologist to help you confirm the red lines to help the physician plan these doses. So in summary, which is pretty simplistic, I'm sorry, just to give you the bottom line, if we ask the question, high LET advantage for this assortment of ions, we found that there were very minimal differences between protons and helium, although there were some measured differences. But it was when we got to carbon, neon, and silicon and argon where we saw significant increases in the RBE and reductions in the OER. And the physical depth dose was superior for these two. So clinically, we focused on neon and carbon in the clinical work that was done in this period. And the results from the neon, which are summarized in this work of Dave Lindstedt in 1991, show that several tumors, I think 5 or 6, showed to be very responsive and were compared to conventional neutrons or X-rays. And they included salivary gland tumors, which showed only 30% responsiveness to X-rays, but showed in the 60% range for both neon and neutron ions in effectiveness and eradication. Also sarcomas of soft tissue and bone and locally advanced prostate disease were also shown to be advantageous. Now, these were phase 1-2 trials, which means we missed the opportunity to finish a phase 3 trial before this program reached its closure. And we were happy to know that following our closure, which happened in 1993, the work went on first in Japan and then in Germany and then the rest of the world. Now, what people often ask is how does this work? Why is this so effective? And that part of the story brings me to this discussion of particle tracks. These are tracks that are visible in emulsion, photographic silver emulsion. And this is the work of Harry Heckman, where you can see the ion coming in on the left and stopping on the right. This profile is illustrated in a schematic way here. This track structure actually means that any single particle beam that you use is already a mixed LET beam. And that's a very important concept to keep in mind when treatment planning of these ions, that you actually have a complex core, which is very dense high LET, but you have it surrounded by a penumbra of low LET tracks of delta rays, which are of low LET. And the ratio changes depending on where you are in the attenuation of this beam, but it's important to the effect. And the schematic cross-section illustrates that most clearly from the work of my colleague Alok Chatterjee. And so the business end of this beam is here, but there are actually, from what we understand about effects of targeted and not targeted effects now in biology, the importance of this is very significant. Now, when these different tracks cross DNA, you can't but help to know that there's going to be differences. And I like to think of each of these single tracks of carbon, alpha, and protons in this illustration by Dr. Belli in Italy showed you that the bottle brush cleaner for baby bottle brush cleaner is very thick here for the 1 MeV carbon and even the 0.3 MeV proton. But at higher energies, it's a cleaner bottle brush cleaner. And it shows that it doesn't have as much chance to interact with tissues or molecules in the DNA. So I know I've gone through this very quickly, and I'm happy to answer questions at the end, and also to provide any papers you might need to understand it further, but it's all about the tracks. Just remember that. If you compare protons and neon at the same LET, for example, at 30 keV, the ion beam with the lower charge, the 1 MeV proton, has lower velocity and smaller track radii compared to the beam with the higher atomic number, which would, in this case that I just illustrated, would be the 377 MeV per AMU neon. So more energy is deposited by the lower energy ion in a smaller target volume, but more target molecules are hit by the higher energy neon beam due to the delta ray dose. So this leads to both qualitative and quantitative differences between protons and neon. Now, what happens after the track passes is the production of ROS, oxidative species, radiation-induced oxidative species are produced primarily from the oxygen being there. And if without the oxygen, you get a different spectrum of ROS, but heavy ions and other high LET ions produce these oxidative species, chemical species, that are distinct from those produced by low LET. And this leads to all the high LET effects that we see related to oxygen enhancement ratio, cell cycle dependence, changes in transcription, changes in production of responsiveness of promoters, and also development of distinct protective mechanisms. And there are still very many uncertainties, however, at low dose. So what makes the particle radiation so effective in summary? Well, I believe it's the track structure and the fact that the damage presents as clustered damage, triggering different damage and repair pathways than low LET radiation. We also see shattering of the DNA, which does not happen with low LET. So the production of short DNA fragments, which have slower repair and the evidence of misrepair, as well as genomic instabilities and microenvironmental changes in the tissues, including both the stem and immune compartments. And we absolutely know the LAT-dependent gene responses are different. So my personal perspective is that we need new scientific approaches now to investigate the underlying mechanisms further and in different biological systems, because each tissue may in fact be different than the others, to investigate improvements in the anatomical and functional imaging of normal and tumor treatments, which is an essential tool in the treatment, and to develop novel ion beam delivery and treatment planning tools and mathematical and biophysical models to personalize medical care for individual patients in the treatment of their disease. And to do this, we need a team of people that, like you all, that are competent to work in this field. And that is not trivial in this world, because they're not training enough people with this background, to my opinion. Now let's take a more global view. You may not know it, but recently Dr. Sung published a global report on the incidence of cancer in the world. And up here on the left here, you can see that globally he reports in 2020, we had 19.3 million new cases of cancer reported and 10 million cancer deaths. And globally, currently in the 2040, he's predicting a 47% increase to 28.4 million new cancers. This is a grim statistic. And when you look for particle beams to see how they would be available to the world to use as a tool to eradicate these tumors, you can see that there are a total number reported by PTCOG of 279,000 patients as of the end of 2021 who have been treated with protons. And of those facilities that produced, the operating facilities are now 95, and of which 42 are in the United States. But for carbon ions, there have been now a total number of patients, 41,294, from 13 operating facilities worldwide, and all of them are in Europe or Asia. So the United States has lost out on that. And there have been nearly 4,000 patients treated with other ions and heavier particles. So we have a lot of work to do. In 2015, the carbon ion program was reviewed in Japan, and I was honored to participate in that review. And they now have completed well over 20 years in 2015, and now it's going to be even beyond that. But radiobiology needs still continue. And what people are working on in the field at the present are evaluating risks of secondary cancers and late effects. And this applies not only to cancer therapy, but to other particle exposure opportunities, such as appears in space travel, where crew are exposed to multiple ions simultaneously. And we need to identify the radiosensitive patient who could be treated with a more conservative treatment plan. We also should try to reduce an unnecessary dose outside of the treatment volume. And that would be important, especially for pediatric patients who survive, to make sure there's late effects that do not interfere with their normal life. And there's also quite a need for specific chemotherapies to be explored with particles. I've done a little bit of work in that field, but much more needs to be done. And the fractionation regime and its impact is important also to the decision of how to do the treatment planning. And the question I get all the time is, what is the best biological model for validating dose effectiveness? That's a moving target depending on what the question is that you're asking. So the factors that have been hampering heavy hadron work, in my view, are the lack of clinical phase 3 trials, which are needed for approval by different countries, the cost to build the carbon ion clinical facilities, the current lack of US insurance reimbursement to maintain a carbon facility, and the lack of international consensus, which currently exists on treatment planning methods to facilitate comparison of clinical trials. In summary, the Hadron therapies have unique physical deposition patterns and some novel characteristics of the biological response depending on the radiation type and quality. There is a need for further basic biological investigations to clarify the significance of these unique lesions at all levels, molecular, cellular, and tissue. And now we have many powerful new technical tools and genomic and proteomic resources available to radiobiologists to study these effects. It's a very exciting time in the lab. Theoretical modeling of expected Hadron biological effects is also important to optimize treatment planning, and the future scientific opportunities for Hadron therapy, in my view, are quite promising. The material I presented to you in this presentation is intended for your personal edification. If you need to or have a desire to use some of it, please only after contacting me. And I'd like to show you the 184 accelerator now and its new life as an advanced light source. And thank you for your attention and the invitation to give this presentation. And I'm eager to answer any questions. Thank you.
Okay, I guess we can start doing the questions and answers. I saw the first question from Manjit.
It was not a question, just to say I really enjoyed the talk.
Okay.
The questions are for students, and if we have time, I would like to ask a couple of questions,
Okay.
but not until the students finish.
Okay, I guess while we're waiting for some live questions, there was actually some questions in the Google Forms pertaining to your presentation. So since you gave the historical perspective, then like one of the questions that we got before the course would sort of be, what are the radiobiological questions that have still not been answered if we are looking at heavy ion therapy? What is like the main things that we need to know?
I think I covered that in my presentation, but I'm happy to say that we still have not converged on a single theoretical model to evaluate responses to different biological effects from different ions and tissues. And I think it's really important to work with a physicist at the bench together to solve that problem. And there are some excellent models, and you can see our very simplistic approach. We actually devised a model which Professor Tobias called the repair and misrepair model. And we also used alpha beta linear quadratic model. In this simple lookup table, we had very minimal toxicities in these heavy ion patients. We didn't have a very high patient number because the work of treatment planning in this experimental venue was extremely time consuming to be safe. But for safety, we really need to open up and understand the differences at different dose levels and dose rate levels. And now with FLASH emerging as another option for the future, for example, FLASH radiotherapy is a very high, fast delivery of high doses that can perhaps protect normal tissues. It also is conducive to not having to restrain the patient so much when you can deliver a single dose in a very high dose fashion. However, there are risks involved in that. And to assure safety, a lot more work has to be done before that can actually be implemented, in my view. That was why I actually began the presentation talking about the historical approach to use heavy ions, or protons rather, and helium to treat these unique lesions of the AVM and uveal melanoma. And the 20-year follow-up is very important. And those kind of data clinically are what contribute, but they can only be made with the biologist assuring that's the case for each individual tumor. So is a lung tumor the same as a pancreatic tumor? Is a prostate the same as or are there cardiac effects when you treat the lung that you have to worry about? Those kinds of questions are important as well. And even more elementary, is at the molecular level, this cluster damage, why does that happen? Is that as a result of the target, or is it totally an overlap of the structure of the track as well as the structure of the target? And, you know, is it every part of the DNA molecule that gets the same clustering? We have still many questions we don't know the answer to, and it's wide open and very relevant to the clinic. I hope that answers your question.
Question from Rebecca. We don't hear you.
I think you're muted.
Can you hear me now?
Yes.
Yes. Thank you very much for that really interesting and really clear talk. You had some plots with the track structure of the particles to show that the center of the particle track had a high LT, but the halo around it was lower. Is there anything that the providers of the particle beam can do to provide something that's more uniform, or is it just a fundamental part of how these particles are interacting?
Yes, that's a very good question, and probably touches in an area I should have spent a little more time on. You would, after hearing my presentation, you would think I'm very fond of LET. And it's not just because people used to call me LEB, but one of the things is that LET has also some weaknesses. And you can have the same LET with two different beams. If you go back to that plot I showed you where the peak RBE was, and the three lines came down, each with a different ion. If you draw a vertical line at an LET, that means you can have two different data points at different RBEs with different ions. So LET has deficiencies in its ability to capture what is important. So many people have resorted to testing two things. One, it's very clever. This has been started by Neil Basler and others, where they actually look to map LET in the field covering a clinical trial, like let's say a tumor target, and see if they get effects where the high LET is greatest. But that doesn't always match with the outcome. So mapping LET is not completely the answer. And so what that has led to is the conception of other models, of which I'm a part of a colleague who's working in this field. And he hasn't completely published everything, so I have to be careful, but there are other features of physical features, which is what I think you're asking me, that can be used to evaluate the clusters in a different way than LET. LET, you know, can be linear energy transfer, can be calculated by dose or track average, depending on how you do it. And even doing the different plots shows the difference. So the clustering seems to be the key to what we think is important. But you're very right to ask that question. That gets to the heart of the problem. Thank you, Rebecca. Please don't be shy. I'm happy to answer any question you might have.
Don't seem currently to have any questions from the Slack or in the chat. From the chat, it's just a comment to you. Thank you for the thought-provoking presentation from you.
Oh, I'm glad you liked it.
Yeah.
So may I ask a question then, Christoph, if there's no other questions?
No, I don't see anything, so I suppose yes.
I could ask Ellie, obviously offline. So Ellie, have two, but the first one, and unless a student asks something else, as you said, is all about tracks. Well, whether you use flash or normal, the tracks are the same for all the particles. So what's going on?
Yes, that's a very good question. But is the target the same? It turns out the difference in flash is comparing normal cells and tumor cells. And the microbiology of, I would say the microdosimetry of that target may be quite different. We know from a lot of other work in the field of cancer research that when a normal cell goes bad, it becomes a cancer cell. It changes its metabolism, for example. And that creates a whole array of molecules that are different in the tumor tissue compared to the normal tissue. So in the early days of FLASH, when people were reporting no in vitro effects, because they were doing it in a petri dish that ignored this phenomenon, I kept saying, why are they publishing all these data that don't show a difference between normal and tumor? It's because they don't really have the capture of what a normal tumor looks like in terms of the molecules. And so we are now looking into molecules like lipids and iron molecules and modes of death, because the type of, when cells are killed by radiation, we used to simply think they just necrosed. Well, it turns out there's a whole array of different ways to die. And they each are triggered molecularly by a different mechanism and different pathways. And so it's hard when I work with physicists, they are very smart, and it's very stimulating and challenging to work with. But what I find is they have trouble to conceptually understand molecular pathways and how they work and how they are decided upon by the system that directs it.
Yeah.
How do you know that's going to be that way? Or if the cells are distributed through the cell cycle in a different way in a tumor, is that important? There are so many fundamental questions we don't know about FLASH. I mean, I'm a proponent of the research, but I don't think we should jump into the clinic just yet.
So I couldn't agree with you more, because, so far, we know from everything we know about radiobiology, and when cells are radiated, there's no such a thing as no effect and no harm. Okay. And this is always a big challenge, because we are talking about FLASH saying healthy tissues are protected, tumors are, selectively killed. But what is it that's really happening? Because we don't understand.
Yes,
that's one thing. And the second thing is your point about lipid peroxidation. Well, it makes an awful lot of sense. About 30 odd years ago, we were talking about lipid peroxidation and calorific content, and people who either fast once a week or have a lower calorific intake, they live longer. So, if you see what I mean, I think there are all sorts of things to think about, and what we knew in the past and how do they come together.
And the other thing, yes, I totally agree with what you just said, Manji. In addition, I would like to comment about the fact that I've been working the last 6 years in the area of tumor induction, and those responses are a part of that measurement. However, when I tell people that it's low doses that are very important, the clinicians, that's where they scratch their head and they say, well, low doses don't do anything. Au contraire, it turns out that there are epigenetic effects at low dose that are critical to a late outcome, especially for late consequences of radiation effects. And this has significance not only to NASA, for whom I did the work, but the clinic as well. But it's hard actually to defend a grant to a clinic based on low doses, but it is very critically important, because the operating mechanisms are different at different dose levels and dose rate levels.
I'm sorry. There's a student, so I come back and go back.
Hi, I'd like to thank you for a very interesting talk. I really enjoyed it.
Thank you.
And then my question is going to actually be an opinion-based one. So it's actually regarding in vitro studies, because I personally feel that it's very easy, in fact, easier to miss a lot in an investigation than it is to actually properly nail down your study to a point where you've adequately answered your research question, just because there are so many ways to investigate one mechanism, whether it be assay-based or the system you're looking at, molecular or cellular. So in your opinion, what would you say would actually be a few central things that are absolutely important to look at when you structure your in vitro studies?
Very good question. In vitro is very elucidating of the beginning of the story. But when you have a flat cell on an artificial surface, it's not a normal situation. Cells don't usually grow flat. They have spherical tendencies when they're in real bodies. So even the passage of a track through a flat cell, the tissue at risk through the flat cell is minuscule compared to the track that goes through a spherical cell. And so that led to the realization of that difference, led to people growing cells, single cells, in spheroids, in balls, and the tumors do balling very easily. And you can, many normal cells won't do balls. They won't grow. What happens in tumors, again, is that their adhesion molecules are different than in normal cells. That's why tumor cells frequently have a higher density, and you detect them by actually palpating hard tissue. That's a bad sign for cancer, hard tissue. So texture changes, and that also affects the targeting for radiation. So I'm not giving you a simple answer, but what I'm saying is the approach has to fit the question. So if you're asking also about tumors and you don't have hypoxic cells, then you don't have the microenvironment that changes with cytokines being different, proteins floating around. And there are also morphological changes in architecture of normal cells when they become a tumor. And you have to really synthesize all of those changes in a model. So if you just think you can simply take a chunk of normal tissue and a chunk of tumor tissue and compare them without controlling the ambient temperature, the atmospheric pressures, the oxygen concentration in the ambient air, which changes the pH, and the pH changes the metabolism. It's the right foot's connected to the leg, and everything's connected. I don't have a simple answer for you because we don't know. Again, all these in vitro things are models, and they model one aspect of the normal tissue and the tumor tissue, but they don't capture usually the whole story. So you can actually get the wrong answer to the question if you pick the wrong model.
Sure, for sure. Thank you. That's adequate enough for me, I must say, because it's really, I knew it was a difficult one, but I figured I might as well ask it because it's very important to have these conversations, in my opinion.
Yes, the simplest thing I can tell you is when I've done a whole lot of work with lens cells, human lens cells. And when I first acquired human lens cells it was actually a fetal source of a mother had lost her baby and donated the tissues to me. I learned that I couldn't grow them on a plastic petri dish. So I worked in a laboratory where the director was Dr. Mina Bissell. I don't know if you know that name, but she really promoted the use of extracellular matrix on plastic petri dishes to grow tumor cells. And she had a tumor cell modeled from a mouse. And so she already had plates which had this matrix on as a substrate on the surface. And so I said, well, if I can't grow my human lens cells on this matrix, I should be able to grow it on hers. So I put the normal human lens cells on the tumor mouse matrix and let them grow. And they went from beautiful lens forming cells to starlight. They became stellar in formation. Completely wrong signaling of molecules adhered to the matrix. And they were tumor signals, not normal lens signals. So then I realized I had to go to the cornea, which is the next normal tissue adjacent to the lens. And I then acquired tissues from a a bovine source from our slaughterhouse. I had to get a special permit actually to go there to collect the eyes of the cows after they were taken for meat. I harvested the corneal endothelial cells and grew them in petri dishes and added dextran and learned how to create a matrix from a tissue, even though it was a different species. It was adjacent anatomically to the lens. And I was able to grow, and I can send you the paper. The new lens cells grew beautifully on this matrix. What you do is at the end of production of the matrix, after you add the dextran, you lyse the bovine cells. So it's like a cobweb network. It looks like French lace if you stained it with methylene blue. It's a beautiful situation. And the signaling was more normal to the lens than was the tumor of the mouse. And we were able then to ask some very fundamental questions about how human lens cells respond to radiation.
Thank you very much for that wonderful answer.
I'm sorry that it entails quite a bit of work.
No, I can imagine. I can imagine.
You have to be creative and thinking about the question you really need the answer to. That's the key. And once you know the question you're asking, then decide what the best model is. And you will be the best person to decide that.
Thank you so much. That's more helpful than I can begin to describe.
I don't see anything in the chat. Actually, I wanted maybe a question for myself.
Please.
But it's a bit, I guess, on the physics side as well. But sort of when we go heavier and heavier in ions, and like the beam becomes more mixed and mixed with all the fragments. So sort of already there's the physics associated uncertainties in the fragment production, and I do imagine there are a lot of uncertainties in the RBE calculations. So sort of what would be, I don't know, the estimates of like the uncertainty level if we go to carbon or even like the argon and neon, like sort of how sure can we actually be in those models? What would be the uncertainty estimates there?
Yes. We should talk about error analysis, because what you've touched upon is a very important feature to know how well you know the measurement you're making, how tight it is to the real world, and what do you use as a comparison. And when we started doing this work, for example, we would pick a beam of carbon and neon to compare, but that meant that they had different initial energies to achieve the same depth of penetration. And it was very important in my mind to pick the different energies tuned to the same depth of penetration for that comparison. And I worked with Professor Tobias in our paper from 1979 to actually do error analysis, which in itself is a whole discipline, I might add now, because it actually gives you a clue, depending on the tightness of those fits of your error estimate, which is really the truer story. It's a clue, but those are difficult mathematical things because you're taking ratios of ratios, and that's not trivial mathematically. But nevertheless, the answer to your question of how much error is involved in the RBE is lots. And most people, if you look at the literature, don't even report error very much unless they've had a physics background. And that's hampered the field, that the biologist is afraid of doing the statistics or hiring someone to help them do the statistics, or even finding a statistician who's competent in the physics world in that field. It's not trivial either. So what you really need to find is a resource. And the way you find it is you've looked for in the literature for a paper that approaches what you're looking for. I know as an associate editor of several journals that that's one thing I always do. If I get a paper in a field I'm not even familiar with myself, I look at the literature and I say, well, who's really doing the most cutting edge work in this field? And then how do they do it? And how do they, because they always have error. And is there dosimetry reported with a reference to gold standard radiation? Because another thing that's missing is they say, oh, I'm using protons. Oh, great, but what energy protons? The RBE changes with the energy of the proton. And you need to know that. And that's not something a biologist would be able to measure. They would need someone to help them. So the whole story of error analysis is exceedingly important to this science, in my view. I don't know if I've answered or just rambled here, but does that answer your question?
Yeah. Thank you. But it's in the end, it's like it does scale up. Like, sort of the error levels are a bit lower if we are at like protons, and it's the error bars are like quite larger if we approach like oxygen, neon.
Yes,
as uncertainties grow with the atomic number, I suppose.
they do. Actually, what I learned working with carbon, for example, and neon in comparison was they were similar at short range at 14 centimeters. But if I went to 24, then the neon was better because it actually provided a higher LAT uniformity at depth compared to the carbon. So if you're treating shallow tumors versus tumors at depth, also another dimension is I was working with patients who had breast cancer. And I worked with a couple of engineers, and of course, we said we're going to have a breast cancer patient. So they built a device to have the woman's breast in this field. And they went to a book and looked up the average weight and height of a woman and built the device for that. And of course, the first woman we had was 3 times that weight and height. She didn't fit in the device. So, I mean, this obesity, unfortunately, especially in my country, is rampant. And it's not a good thing. But how it's an engineer's approach versus a biology approach. We really need, when you have a tumor at depth in such a breast, it's different physics than if you have a smaller tissue. It's the same thing as comparing the effects of a radiation on a child versus an adult. The scaling matters. And to protect the child, you have to scale it down for it to be representative for any studies you may have done at higher energy.
Thank you so much for that.
So Ellie, we've really enjoyed listening to you. As you see that the students are fully engaged. I think what is important, what is really important is the thought process, is the balancing of doing things and how field moves and still reflection. So I really appreciate and thank you on behalf of the students, also for talking to us on the 4th of July. And next year, we are going to be doing a course on clinical aspect, on the physics aspects. So we may call upon you again, because now we start talking about the clinics. And so thank you so much. I let you go before George kills me. Okay, and maybe we discuss another time. So thank you so much. Really appreciate you taking the time and talking us through the logic of where we've come from and where we are going. Thanks a lot.
We need you. Bye.
Thanks a lot.
Bye. Thanks a lot.